Welcome everyone to tonight's little presentation on chemistry of the universe. If you were here last month, I talked about the chemistry of space and talked about how we do chemistry in space and how we look at instrumentation to look at planets and comets and all these other wonderful things out there. But this time we're going to take a little different path. And instead of looking at probes and landers and stuff, we're actually going to look at the interstellar space and look at things like stars. And when we look up at the night sky, I just think this is a beautiful picture to look up there, and we're just always been fascinated with the night sky, with the stars and the nebulas and the planets and everything that are up there. And we've always looked to the sky and really revered it. You know, if you think about the ancient civilizations like the Greeks and the Romans, they named their gods and their heroes after the stars and constellations. Ancient travelers used the stars to guide them along the oceans and along land. So there's always been a fascination with the stars and everything that's up there. And with this fascination, there's always become a question. How are we related to the stars? How are we related to the things out there in the cosmos here on Earth? How are things put together? How do we relate to this great vastness? So to do that, I want to actually start off talking about where we're at first. Whoops, I have not been drinking yet. Looking at this big purple or big blue marble, all right, that was taken by Apollo 17 in its trip out to the moon. And when you look at the Earth, we can find that the Earth is made of about 3 regions that are very important to life on Earth. There's the atmosphere, which is made up of nitrogen and oxygen primarily, with other things like argon and carbon dioxide and water vapor. And then there's the oceans, which is basically we take some hydrogen and oxygen and put it together and make water. And then we have the mantle and the crust, which is made up of things like oxygen and silicon, which makes sand, and magnesium and iron and nickel and cobalt and all these different metals. So when you look at the Earth, we find that we have the 3 phases of matter, solid, liquid, and gas. But the question is still, how is the Earth related to everything out there? How are we related to everything out there in the cosmos? And when we talk about things like that, one of the things we can look at is the stars that are out there. The stars were the easiest things to study when we started studying the outer space. And we did that by looking at the light from stars. Now, if you were here for the talk last month, I talked about how you can take light and split it up. And when you split light up, you get a rainbow. But if you take light from a star and split it, you get what we call a spectra, which are not a rainbow, but individual bands of color. Now, these individual bands of color give us a chemical fingerprint of the star. If we see something for oxygen or carbon or whatever, we know that the star has these elements. And this is an actual spectra from the 1920s from the star Arcturus. And as you look up there, you can see that the elements in the star match a lot of the elements we find here on Earth. Let's see, there's some iron, and there's some sodium and calcium and carbon and nitrogen. There's some silicon. So there's all sorts of elements that we find on Earth out in stars. So there's a relationship between the Earth and the stars. And for the longest time, scientists believed that the Earth and the stars basically had the same composition. The only difference is that stars varied in what was there. Some stars had more iron, some had more carbon, different things like that. It actually wasn't until the 1920s, this lady right here, Cecilia Payne, working on her PhD in astronomy and physics, basically in her paper was saying, you know what? I've been studying stars and their composition, and I've been studying how temperature is related to their composition and their color. And I've come to discover that stars are not like Earth. That stars are actually 90% hydrogen and 10% helium, and the rest of them are just kind of there. Now, this right here was a big blow to the scientific community because they're like, no, wait a minute, hold on. No, that's not true, because we can look at spectra and see that there's a difference. It wasn't until further study that we found out that no, The universe itself is 99% hydrogen and helium. 99% of the universe is hydrogen and helium. Just two simple elements. So now you're probably going, okay, where did all the others come from? Where did carbon and nitrogen and oxygen and phosphorus and sulfur, all the things that we need for a biological system to work, come from if the universe is 99% hydrogen and helium? Well, to do that, we're going to take a step and we're going to actually start off looking at those two elements, hydrogen and helium. We're going to do a little simple introduction to a little bit of atomic theory, and so we can talk about the chemistry. Now, hydrogen and helium are the two simplest atoms in the universe, all right? Hydrogen has one proton and one electron. Helium has two protons, two neutrons, and two electrons. So every atom is made up of three fundamental particles: protons and neutrons, which make up the nucleus, and electrons that orbit in a cloud. Now, when you think about an atom, inherently it shouldn't work. A nucleus is made up of positive protons, and what happens if you take two positive particles or two ends of the magnet that are the same and you put them together? What happens? They repel each other. So in theory, the nucleus of an atom shouldn't hold itself together. Same thing with the electrons out in the clouds. They should fly apart, but they don't. And that's because there's something known the strong nuclear force. And that's what holds that atom together. Now, when you're looking at atoms, we find that every proton, every neutron, and every electron is identical. The only thing that distinguishes different atoms from each other is the number of protons that are present. One proton is a hydrogen, two is a helium, three is a lithium, but otherwise there's no difference. So if I want to make a new element, all I need to do is change the number of protons I have. Okay, so this is a great idea. Let's take this atom, and let's try to put them together. But those electron clouds that orbit those atoms, those nuclei, keep the atoms from getting close. So that strong nuclear force that binds things together can't hook onto the other atom and pull it together. So we got to get rid of electrons. How do we get rid of electrons? Well, a star has a perfect capability of doing that. A star is high temperature and high pressure, and the result is all those electrons around those atoms get what we call ionized. They get completely stripped away. The electrons just go away, and all that's left in the star is just the nuclei of all those atoms, just the protons and neutrons. So now you're talking about this big, gaseous, very hot, high-pressure star that is mostly hydrogen atoms, and we're allowing those hydrogen atoms to get close to each other now. And what's going to happen under high pressure and high temperature? A process is going to happen that doesn't happen here on Earth. A process that we would like to happen here on Earth if we could control it, but we can't quite do it yet. And it's called thermonuclear fusion. And in thermonuclear fusion, what happens is we take some hydrogen atoms. So we're just taking those little protons. High pressure, high temperature, lots of pressure, getting them close together. That strong nuclear force grabs them and hugs them. And we turn 4 hydrogen atoms into a helium atom. Now you probably noticed something here on the screen that I start off with 4 protons and I end up with 2 protons and 2 neutrons and lots of energy. That's the energy we're feeling every day from the sun in this chemical reaction. Now this is a reaction that we can't do here on Earth yet, but it would be nice because we get rid of all that radioactivity and get lots of energy out of it. But this is the process that stars undergo. So let's think about what would happen now if we take a star and let it live out its lifetime. All right, we start off with a star that's mostly hydrogen, starts converting things into helium, and at some point it runs out of hydrogen. We go through what's called stellar evolution. Stellar evolution, where we start off with a hydrogen star. It's going to be just like our sun, converts hydrogen into helium. At some point, though, we're going to start running out of hydrogen. Hopefully not anytime soon with our star, because that might kind of be a bad thing. I think it's scheduled for another few million years. I think we've got time. Then we start making helium atoms. All right, at some point now we're going to start running out of helium atoms. The star is going to continue to get hotter and hotter. The gravity is going to increase and increase. Now we're going to start fusing helium atoms together. And when that starts happening, we're making even heavier atoms. We're looking at making things like carbon and nitrogen and oxygen, things that are very, very important to life on Earth. So over time, you have a star like ours, a yellow star, or turn into a red giant. And a red giant, in its final stages of life, is basically like a big jawbreaker with different layers. And inside each of these different layers are different atoms that have been made throughout the course of thermonuclear fusion. We start out with hydrogen, made helium. Helium makes carbon and oxygen. There's some nitrogen in there, some neon. Then we start making even heavier things like phosphorus and sulfur and silicon. And then we get to where we're starting making metals, iron and nickel. Now, unfortunately, when we get to the point where we're making iron and nickel, the star is in its last throes of life. All right? At that point, it can't produce enough gravitational pull. There's not enough energy and pressure to fuse iron atoms anymore. So the star is going to start to die. And when the star dies, it does it in a spectacular fashion. It does this, a supernova. So now the question is, or now that we can kind of answer the question, all right, this is a very good question. This is actually still photographs taken from the Hubble telescope from 2002 to 2004 of a supernova as it was exploding over several years. So these are just a composite of about 2 years of pictures showing that explosion. All right. I don't remember off the top of my head, unfortunately, which one it was exactly, but it's a beautiful. Which one? Thank you. I'm not an astronomer. I'm a chemist, so I kind of forget things like this. All right. But the whole idea is now we've got this star that was in its last throes of life. It's got all these extra atoms in it that's been made through this fusion. And now what just happened to it? They've just been scattered into the universe. All right, so these have been just scattered out into space now. So now we've got iron and nickel and carbon and oxygen just floating around. Okay? So there's this cycle that goes on. All right? And it's a repeating cycle. This star evolution is a repeating cycle that goes on and on. We have these nebulae that are very rich in being able to form stars, lots of hydrogen gas. They coalesce and make protostars. And then they can either become yellow stars like ours, or massive stars, red giants, super red giants. And at some point, they're going to explode.
Wait a second, yellow stars are sun?
Yes, sun-like stars are like yellow stars. Yeah. All right, so then, we get to the red giant. It explodes. We have a planetary nebula. It's rich with material to make planets. This is how they theorize that our planet was made, was something like this. A yellow sun like ours become a red giant, then exploded and created a planetary nebula, and then it condensed to make our own Earth, which has all those different elements that we've seen in the star right before it dies. So this idea that where we come from is actually from old stars leads us to think about what other types of chemical reactions could be going on and out in space. And when you think about those, think about what's going on out there. We've got these stars and these nebulae, and we've got dust particles and all these things out there in space. And we have this idea of it's very cold, but there's also high amounts of radiation. So what the Ames Research Lab at NASA has done, and when I was doing my research for this, I did a lot of reading from Ames, is they've created a chamber where they can simulate what's going on out in space. And they try to seed this chamber with the things that we would find out in interstellar space, like these carbons and these other elements, and oxygen and nitrogen. And we're trying to see what type of reactions go on when we are giving them their radiation in this vacuum of space. Now, at the same time, they're also being irradiated from the stars with heat and light and so forth. So let's talk about what the star just give off. All right, so the star just exploded, and now we've got some carbon atoms, some oxygen, some iron, helium and hydrogen, nitrogen. Well, these atoms now have gained the electrons that they need to be stable out in space, and they're going to start bumping into each other. They're going to be irradiated with energy, and what's going to happen is in the interstellar space, we're going to start seeing simple molecules formed. Water, carbon dioxide, a carbon and cyanide compound, carbon monoxide. They actually can do this at Ames. They actually take their reaction chamber, seed it with these elements, irradiate it with high energy, and they actually start forming these simple molecules. Now, these simple molecules have just been exploded from a star. They're traveling through space. They're going to eventually start running into things, especially if you're out in a nebula. So we're out there in a nebula, and it's going to start running into little dust particles. Now, these dust particles it runs into are about the size of a molecule itself. They're not like the dust you go dust your bedroom, okay? Anybody that wants to go dust a bedroom, mine is ready, that needs to be cleaning at this point. All right, so you've got these dust particles, and they're going to start absorbing these molecules. And as they absorb, they give them sites for reactions, where these simple carbon monoxide, carbon dioxide, and water can start forming bigger molecules, like alcohols. We can start forming things like methane, ethane, more complicated, simple carboxylic acids, things that have a couple of carbons bound to them. So we're looking at the ability to make simple molecules, all right, out in space on these dust particles. Now, as these dust particles are flying around, of course, they're going to be irradiated, they're going to break apart, and now I'm releasing more complex molecules out into space. And one of the most interesting molecules that they have found out in space, out in the interstellar nebulas, is this one, glycoaldehyde. Now, you might wonder why this one is so interesting. Glycoaldehyde is the precursor for things like alcohol, sugars, simple carbohydrates, things like fat, things like carboxylic acids. Very simple molecules that are very important to the function on Earth. So like I was saying at Ames, what they did was they took and made this chamber and irradiated this chamber with these molecules. And two of the molecules that they found very interesting that was made were these two, glycine and alanine. Can anybody tell me what glycine and alanine are? They're amino acids. They're the two simplest amino acids that are found in the human body. There are about 20 of them. Well, guess what? In their experimentation, they have found that these simple amino acids can be formed in the interstellar medium. In fact, in some cases, they believe they have found their atomic fingerprints. That's kind of freaky to think about, right? That out there in space, we're making simple amino acids. It's kind of cool. Of course, when we're out there in space, like I said, everything is always getting irradiated with lots of high energy. All right? And one particular molecule that is or atom that's very important to us here on Earth, how we define life on Earth, is carbon. And of course, carbon is an atom that is made in that star's lifetime as it goes along. And as carbon is flying through space, it's being irradiated with high energy, and carbon becomes what we call a radical. Now, I'm just showing nice, pretty pictures to talk about the science, but this is where it's going on. It's out here in these nebulas and these dust clouds where there is lots of energy, lots of radiation. So we're taking a carbon, we're making it a radical. And what a radical means is it's lost an electron. Now, we're used to radicals here on Earth. This type of chemistry takes place all the time here. How many of you have been to LA? How many of you have experienced smog? Smog is a direct result of radicals. The energy from the sun breaks atoms apart, makes them into radicals where they've lost an electron, and radicals are extremely reactive. They will bind to anything. So on a day that's hot, lots of cars, lots of carbon dioxide, carbon monoxide, you start getting that fog because you start getting these really bad reactions that you really don't want in LA. Well, out in space, those radical reactions are not so bad because they're going to react with anything it can find. This radical carbon is going to go out and find some oxygen to bind with, some more hydrogen, maybe another carbon. So the reactions that go on out of space are a lot of times very simple reactions that lead to very big molecules. And I want to actually show you, this is the first time I've done this, and I never do this when I talk in public, is actually show a chemical reaction, because usually when I do this, people run screaming. My students run screaming when I do this. So here's an actual chemical reaction. Yes, go run screaming if you're running screaming now. All right, so we're going to start off with a very simple molecule that actually gets formed in those dust molecules. All right, methane, CH4. Same stuff that cows make, if you've ever been in a pasture. Okay, that nice smell you smell is methane. All right, now methane is going to get hit with high energy radiation out in those nebulas. And what's going to happen, it's going to actually knock off a hydrogen and it's going to take one of its electrons. So I get this guy right here. All right, that is called a radical. The little dot there is that actual lone electron. Now electrons are kind of like me and my husband. We're codependent. Okay? I got to have another electron. That little guy needs another electron. He's got to find another electron. Well, out there in the interstellar nebula, there's lots of different cases where you've got those situations where you've got radicals. It finds another one, and they get hitched. I've now taken methane and made ethane. I've taken methane and I've made ethane. All right, I've made another organic molecule. All right, if I get some high temperatures going, you know, if I'm kind of close to the sun, if I'm out in the interstellar nebula, what can actually happen is I can lose a couple of hydrogens and make a hydrogen molecule, an H2, which is how hydrogen exists on Earth, and I get this guy, ethene. I went from a 2 carbon and 6 hydrogen to 2 carbon and 4 hydrogen with a double bond. I get some more high temperature, some more energy, and I make acetylene. Now the reason this is very interesting, and the reason I thought this was cool when I looked at the Ames website, is because acetylene can be considered 1/3 of a molecule called benzene. Now, benzene is very, very unique. Here on Earth, we can synthesize benzene very, very easily. All right, it's got very unique properties. But what makes benzene so unique in the interstellar nebula, it's not that we're making benzene per se, but because all we really need to do is somehow throw a nitrogen in here somewhere. Say instead of CH3 here, this was NH3, which is ammonia. Throw some nitrogen in here in this process, and we take benzene and we make a molecule called pyrimidine. Now you're probably sitting there going, oh, woohoo, Shane. So? Well, this is so. Pyrimidine is the backbone for uracil, cytosine, and thymine. Anybody know what those are? DNA. Those are the nucleotides for DNA and RNA. Guess what DNA does? It makes life. It makes us. Now guess what? They have found signatures for all 3 of these molecules in space. I'm serious. Ames. They have actually found signatures, the atomic absorbance signatures for these in space. It's not hard to imagine. It's not hard to imagine. Now, the other fun thing that comes about is this guy. Okay, there you go. Anybody know what that one is? A buckyball, a Buckmeister Fullerene. It is a 60 carbon molecule, very stable, but very hard to make on Earth. It's hard to get it all to stick together long enough to actually form that soccer ball look, okay? It takes a lot of chemistry to do this. Guess what? Out in space, not a problem, all the time. For years and years, they have looked at the interstellar medium and they have found a signature they could not identify. An atomic signature they could not figure out what it was. It did not match anything they knew on Earth until Mr. Bucky made this. And they did the spectra. And they're like, oh, wait a minute. This matches this. Holy crap, we're making 60 carbon molecules out in space. If we're going to make something this complicated, it's possible that we could be making all sorts of things out in the interstellar nebula. So what does that have to do with us here on Earth? Well, it has a lot to do with something like this. Anybody know where this is? 67P, that nice little comet that Rosetta and Philae land on. All right? So if you imagine we've got a comet or a meteorite or an asteroid flying through space, flying through these nebulas, picking up these molecules, and then crashing into a planet, what could happen? Life. Well, the interesting thing is this is actually new data. This is actually, I think, about 2 months old, 2015, put out by the European Space Agency, that the instrumentation on Philae has found even more evidence of organic molecules. Things like ethylamine, propanone, propanol, methyl isocyanide. This guy right here is very important for amino acid development. We're finding that we're making very simple molecules that are precursors to things that are needed for life. So when we ask the question where we come from, all right, when we look out in the stars and ask how are we related to the stars, the very simple answer is best described by Carl Sagan. I am star stuff. Thank you.
Thank you, sir. Awesome. So basically, if we're star stuff, then beer is star stuff, right? Oh my God. I knew we were onto something. All righty. So thank you so much, everybody. Give it up one more time for Shane Haggard, Analytical Chemist. Thank you, sir.
Thank you.
Oh, you're very welcome.